Hey everybody, welcome to our video lecture for CNG 100. Hopefully this is only going to take about 20-25 minutes, something like that, so it won't be quite as long as a normal lecture. The topic is the first one that we need in order to handle reacting systems with our energy balance. So the particular name of the topic, if you look kind of up here at the top, we're going to be looking at things called enthalpy of formation and enthalpy of reaction. Specifically, the parameters that we're going to end up deriving are down here underneath me. So we've got things like H's with hats and subscript F and superscript circle and another H without the F and the I, but with a reaction and still a circle and something else and another temperature. We're going to look at the relationship between all of that so that we can then on Tuesday, Wednesday, and Thursday of next week actually use this to help us solve energy balances for a system that undergoes a reaction. But for now, we're just going to focus on those three quantities, see how they relate. And we won't quite be able to get as far as we need to handle a reacting system, but we'll end up being able to get actually fairly close. The only thing, well, let's get as far as we can, right? So to get started with it, the first thing we need to do is just introduce a new quantity. We have a new one. The name of this quantity is called the enthalpy of formation. And this is one that we haven't needed before. You may have encountered it in a chemistry class. It's probably the same enthalpy of formation that you've had before. The symbol that we give the enthalpy of formation is a delta H with a hat, a subscript F, comma I, and a circle. So that's obviously the first one that's mentioned in the list underneath my face here, is the enthalpy of formation. There's quite a few new symbols here that are not like what we have seen before. Let's knock out the easy ones, the ones that are the same. First of all, the hat means the same thing. So the hat still implies that this is a per unit mass or per unit mole. We will almost never see anything other than per mole, maybe per kilomole, something like that, but it will never be per kilogram. We just don't encounter that very often. The next easiest one is probably the subscript F. The subscript F is just to remind you that this is an enthalpy of formation. Almost as easy as that is the subscript I. The I means if you're working on whatever molecule I is of interest, you will have an enthalpy of formation associated with that particular molecule. There's a different one for different molecules. The circle is the new one. We haven't had to deal with a circle before. The circle implies that this is the enthalpy of formation for molecule I in its standard state. And so the standard state means, in this particular case, 25 degrees C and 1 atm. That's what the little circle up at the top means. The other weird one that we haven't had to deal with before, we've seen a couple different definitions of delta, but the definitions of delta here, fortunately we never have to actually use them to calculate anything, but the interpretation of this delta is quite a bit different. It's referring to a before and after state, but the before state is one we haven't seen before. The before state here refers to elements that are in a stable configuration at the standard state. And so this is the way that you would often encounter these molecules if you were to run out into the world around you and actually bump into one of these. So for example, we never just bump into atomic nitrogen. We bump into nitrogen as the form of N sub 2, so 2 nitrogen atoms, and it's in the gas state. If you knew it when you bumped into helium, which we do bump into helium every once in a while, that is monoatomic. So it appears as just helium in its gas state. You know, similarly, oxygen is diatomic in a gas state, etc. So when the delta is talking about an after minus before, the before state is the elements in their stable configuration. The after state is a little bit more, I don't want to say it's obvious, but at least more intuitive. That is the state of molecule I that you're interested in, that you're actually creating. So for example, if you wanted to make carbon dioxide, you could form carbon dioxide from carbon, which exists as an atomic solid under its standard state, its stable configuration. You could form it from carbon with a little bit of oxygen. Oxygen you'll bump into as a gas, and the product of this reaction will be exactly what you want, which is CO2 as a gas. Hopefully you can't hear that door slamming in the background. At any rate, this is considered the after state over here. And both of these molecules are considered the before state. So what's the enthalpy difference between the after state and the before state for a reaction like this? That's the enthalpy of reaction. It's pretty rare that we have to actually calculate the enthalpy, or sorry, that's the enthalpy of formation. It's pretty rare that we have to calculate the enthalpy of formation directly. They're tabulated for, I would say, at least hundreds, if not thousands of different compounds. There are various ways that you can estimate the enthalpy of formation kind of from a first principles aspect or by combining some information from other molecules. We're not going to get into any of that. We're never going to need any enthalpies of formation that aren't tabulated. The tabulated values of the enthalpy of formation are actually found in Appendix D. So I'm going to drag up Appendix D so we can take a look at it and see what these look like in an actual example here. Let me move that down a little bit for you. Here is our, can I fit the whole thing? Oh yeah, fit the whole thing. So this is Appendix D. This is where you'll go if you ever need an enthalpy of formation. Notice there are two columns that are coming with. There is the enthalpy of formation, and the one that we want is this one right here, enthalpy of formation. It's got the little hat, it's got the little circle, doesn't have the subscript I, but it's organized by component I. The one to ignore is the one right next to it. The enthalpy sub C is called an enthalpy of combustion. Very similar process, except it's talking about combustion, and it's kind of specific to combustion, so we're not going to worry about it. The other thing to notice, beyond the fact that it's simply organized by compound, is that the compounds come in different states. So if you need an enthalpy of formation, you need to watch out for the state. So it's either going to be a liquid or a gas for almost everything that we deal with. Occasionally, you will see one as an aqueous solution. Those are things that typically only exist in aqueous solutions if you need them, or as acetone would have as a gas. Or occasionally, you'll see a C on here. C stands for crystalline. It just means this occurs as a solid, as its stable configuration at the standard state. And so if you want to get an enthalpy of formation, you go over to Appendix D. So as an example for this, we've got a concept check that I want you to work on real quick. Let's find out, actually, do we need a concept check just yet? Let's go a little bit further before we get to that concept check. It'll be a little bit easier if we work a little bit more. So how do we use enthalpies of formation? By themselves, they can be quite useful if you're sort of like in a chem lab somewhere and you need to measure these things. That's maybe all that you're interested in is just the enthalpy of formation. Usually we're interested in a different quantity, which is calculated for a generic reaction. So we have to first define that generic reaction. And so for the generic, I think this is the same one that we used earlier in the class. So for any reaction, A plus B goes to C plus D. So the little lowercase letters are the stoichiometric coefficients, and the uppercase letters are the molecules. We can define another parameter, another enthalpy. And this enthalpy is an enthalpy of reaction. So the sub Rxn means enthalpy of a reaction. It's still going to get a circle, and it's still going to get a hat. This enthalpy of reaction is specifically called the standard enthalpy of reaction. So standard is because it has this little circle on it. So the circle still means standard. It has the same interpretation as before, namely at 25C, 1 ATM, and whatever the stable configurations are. So it's the standard enthalpy of reaction. You will occasionally see these called heats of reaction. Don't confuse them with actual heat as in Q due to a temperature gradient. It's just, we used to call them heats, but they're now called enthalpies. So this is the standard enthalpy of reaction. Oh, forgot the word of. For stoichiometric quantities. So if you have stoichiometric quantities of each component, you will end up calculating a standard enthalpy of reaction for them, as we're going to define in a moment. And specifically, this is for stoichiometric quantities and for 100% conversion. So it's a fairly specific type definition, right? It doesn't seem like it would apply to very many cases. Fortunately, it's really easy to calculate. To calculate this value, you sum up the stoichiometric coefficients of all of your species, nu sub I, and you multiply these by their respective enthalpies of formation I. So you'll have a little circle on top like that. This is the beginning of how we deal with how much energy is given off by a reaction. We start that discussion with the standard enthalpy of reaction. Notice it does have a hat on it. We're going to get to the units in a minute. If we just want to calculate one as an example here, let's say we have the following balanced reaction. So you will always need to balance your reactions. If you don't balance the reaction, sorry, the pen went funny there for a minute. Pen seems to be working again. Hopefully that won't change. So ammonia as a gas plus oxygen. Oh, pen seems to be going a little bit funny. I hope that doesn't stop us. 5 oxygen will end up going to a NOx parameter, NO. Oh, I see what's going on. We're auto-saving, and that's why it's jumping in and out. I'll probably have to disable the auto-save in a bit. Plus water. So the balanced part there is given to you. Most of the time, I'll just give you the balanced equation. Doesn't matter. If we want to calculate, the standard enthalpy of reaction, the first thing that we're going to have to do is go look up from Appendix D the enthalpies of formation of each one of these species. And so if I dig those up in Appendix D, I should see that this one for ammonia in the gas state is minus 46.191. Oxygen as O2 in its gas state is one of our reference states, so that will end up being 0. NO from Appendix D will be plus 90.374. And water will be minus 241.826. Be careful with water, really be careful with all of them, that you get the right phase. The units on all of these will be kilojoules per mole. How did I know the units? They're told to us in Appendix D. If I then want to calculate the standard enthalpy of reaction, delta H hat reaction with a circle next to it, I'm going to use that form that I gave before, which is the sum of the stoichiometric coefficients times the enthalpies of formation. So delta H sub F comma I, circle hat. Now I'm going to actually do this particular piece of math. So if we are looking at the stoichiometric coefficient on ammonia, it's minus 4. The enthalpy of formation of ammonia is minus 46.191. And then we add to that whatever we have for oxygen. So its stoichiometric coefficient is minus 5. Enthalpy of formation of 0, so we didn't need that one. And then moving over onto the other side, we would have a 4 for nitrous oxide, and its enthalpy of formation is 90.374. And finally, the last one for water, we have a plus 6 times the enthalpy of formation of water, which is minus 241.826. So as a result, the enthalpy of reaction with a hat, oh, not enough. Enthalpy of reaction with a circle. If we do all of that math, I came up with the math over here. I got minus 904.696. The units are worth investigating. It is over here. evident that they should have units of energy per mole. However, it's not just a per mole. What we have ended up doing, it's always per mole of unit I. Each one of those enthalpies of formation are so and so many kilojoules, per mole of I. So if we take, for example, what's a good one? Let's take water. When we see this number 241, what that is so and so many kilojoules per mole I. The units on the stoichiometric coefficient are moles of I per that weird unit. We've actually seen this once before when we were introduced to it the very first time. Moles reacted. And that is a unit, this moles reacted is the one that's associated with our friend squiggle. And there's a reason for that. We are going to get back to that in a moment. So when you're calculating this particular version of the enthalpy of reaction, the standard enthalpy of reaction, the units that you're getting here are kilojoules per mole reacted. Also notice that it is specific to whatever the stoichiometry was. If I double all of these stoichiometric numbers, stoichiometric coefficients, the enthalpy of reaction, the standard enthalpy of reaction, is also going to go up by a factor of 2. But that'll be perfectly balanced out later when we actually introduce the squiggle to the system. So with that, let's take a quick minute for you to practice this. So I've got a concept check. If you look underneath my face here, try to determine this quantity, the delta H of reaction in the standard state with the little circle, for the reaction that I've given you there. And so I'm going to let you go dig up Appendix D and see if you can do that. I'm just going to wait for about 2 seconds. You should just pause the YouTube video and work on it and then come back to look at the solution. So I'm just going to wait a moment and then go on and actually give you the solution for it. So pause it now. All right, I assume you're coming back so that you can see the solution at this point. So the solution to the concept check that we're dealing with, concept check solution. The value that I ended up getting was plus 597.32 kilojoules per mole reacted. Per mole reacted. The enthalpies of formation that I got for the two compounds, you probably had to search for them a little bit. For the C6H6 in its gas phase, the enthalpy of formation that I found was 48.66 kilojoules per mole. And for the C2H2, which I believe is acetylene, I don't actually remember what that molecule is, also in its gas state was 226.75. So I plugged those into the expression that I had up above and used that in order to figure out that the enthalpy of reaction here for that one was plus 597. There's no way to guess whether or not that enthalpy of reaction is going to be positive or negative, nor does it particularly matter. If you calculate one as positive and one as negative, perfectly okay. Not the end of the world. We will encounter them as both positive and negative in a variety of different situations, so you can get used to that particular idea. We can do some weird things with the enthalpy of reaction. I can't say we actually do this all that often, but you should be aware that it can be done. There's another form of the enthalpy of reaction, which is delta H sub reaction with a circle and a hat, which is the same. So that is still the standard enthalpy of reaction, but sometimes you'll see it with a subscript I. And so what this is doing is taking the old enthalpy of reaction that we just calculated, circle with a hat, and dividing it by the stoichiometric coefficient of species I, and specifically the absolute value of something like that. So for example, oops, did I run off the screen over there? I can't tell. No, you can still see me. For example, we can calculate for the reaction that I just gave you a moment ago with the ammonia and the oxygen, stuff like that. You could calculate the enthalpy of reaction standard with respect to NH3. And the units will change a little bit, the values will change a little bit. So now it would be 904 it was about 7 kilojoules per mole reacted on top. That was the one that we had calculated before. And we divide that by the absolute value of the stoichiometric coefficient for ammonia, which was 4 moles of NH3, oops, not NHS, NH3 per mole reacted. And so as a result, we could express that enthalpy of the standard enthalpy of reaction now on a per mole of NH3 basis. And so that number ends up being minus 226.174. And the units here are now energy, or kilojoules per mole of NH3 formed. And sometimes you'll just see the enthalpies of reaction written this way. Notice that this value, unlike the previous one, so this one has been normalized by the stoichiometric coefficient. So even if you double all the stoichiometric coefficients, that number will be unchanged. This one, however, the one on a per mole reacted basis, that one will change if you adjust all the stoichiometric coefficients. So there's not really a time you ever need to do that. You should just be aware that something like that can be done. More generally, we are interested in systems. Let me scroll down a little bit here because we're running out of a little bit of room. We are interested in systems that do not have 100% conversion. So how do we handle systems if the conversion of any of the species is not equal to 100%? If the units didn't give it away, my mention of squiggle in the class the other day should have given it away. We now calculate a new delta H. Notice every time we sort of remove one step from the ideal case, that standard state, we introduce a new term, but that's because we're moving one step away from that standard state that doesn't really help us very much and one step closer to an actual reacting system. So we define the last of our delta H's that we're going to look at today, which is the delta H of reaction. And that's it. There are no superscripts, there's no hat, there's no circle. But we are restricted to 25 degrees C. Sometimes you will see this written as delta H of reaction at 25 degrees C and 1 ATM. The 1 ATM is implied for this class. All of our reactions are going to take place at 1 ATM. And this definition is a pretty easy one. This one is the extent of reaction that we have seen before. You got to respect the squiggle and draw it correctly. So it's squiggle, so extent of reaction, times the enthalpy that we just calculated, which was the enthalpy of reaction standard. And if you substitute in the previous definition of the standard enthalpy of reaction, what you'll see is that this expands to the extent of reaction times the sum of the stoichiometric coefficients of all the species I times their enthalpies of formation. And so this is pretty close to a usable value. We can now begin to talk about things that do not have to have 100% conversion. That they don't have 100% conversion is captured by our introduction of squiggle. Also notice the introduction of squiggle is why we no longer have the hat over here. There is no hat above our H anymore because it's no longer on a per mole reacted basis. We have multiplied it by squiggle, and recall that squiggle's units are moles reacted. Right, that is the unit of squiggle. And so as a result, the enthalpy of reaction at 25 degrees C is going to have units of essentially just kilojoules, or potentially joules, something like that, because you have taken a kilojoule per mole reacted, multiplied it by something with a unit of mole reacted, and you should end up with kilojoules. If it ends up being that the squiggle is not just moles reacted, but because we are dealing with a flow system, it'll probably be moles reacted per unit time, like per second. This will then become kilojoules per second, which should be a familiar unit of the kilowatt. So that's how all of the units end up working out here. We've got one more concept check for you to work on, which I will drag up over here on the little window underneath me. So figure out what this delta H of reaction is for the concept check that we just did a moment ago, but for a particular reactor. So let me pull up the actual reactor. Goes right here. Scroll that down a little bit so you can actually see the reactor. So what I want you to do here is take a couple of minutes and try to calculate what the enthalpy of reaction is here at 25 degrees Celsius. So pause the system or the video. Yeah, pause the system. Pause the video for a couple of minutes. Take a whack at this one and then come back and I will show you how I went about solving this. TikTok. All right, I assume you're back now because you have solved this particular problem. What we would need to do in this situation is calculate the extent of reaction. Remember, the general definition of this is the moles of any species I that were going out minus the moles of species I coming in divided by the stoichiometric coefficient of that particular species. So we can pick basically anything that we want right there. We happen to know that it's 75% conversion, and we were told that there were 4 moles of the benzene molecule, the C6H6, coming in. And so as a result, we can calculate, using that 75% conversion, how much of the benzene must have been coming out. If you convert 75% of 4, you end up with 1. So there's 1 mole coming out minus 4 moles of benzene coming in, divided by the stoichiometric coefficient of benzene, which in this case is a -1. And so our squiggle here ends up being 3 moles reacted. You could have attempted to do that with the C2H2 as well. Should end up with the same number. And as a result, our delta H of reaction at 25 degrees C, it's important to keep noting that it's at 25 degrees C. Don't drop that 25 degrees C yet. You can drop the 1 ATM if you want because we're never going to change it, but don't drop the 25 degrees C. That particular value, if I use the math that I had before, will be 1,791.9 kilojoules. It's a little bit weird unit. The reason that it just looks like a kilojoule and not a kilojoule per second, which you're going to by far more often use the kilojoules per second, is because up here in the problem statement, we were just told it was 4 moles. More often than not, you're going to see this come in as 4 moles per second, and then coming out will also be 4 moles per second, and so your squiggle term here will be moles reacted per second. And so most of the time you're going to be encountering this as kilojoules per second, which is a kilowatt. The last thing that we have to be able to figure out is what happens if it's not at 25 degrees C. We're getting pretty close. We got in the ballpark with our standard enthalpy of reaction. We got a little bit closer with our enthalpy of reaction at 25 degrees C because now we can account for things that aren't 100% converted. The next one is the only remaining one, and it's the biggest one, which is what if the temperature is not equal to 25 degrees C? And so that's the topic that we're going to cover on Monday. At this point, this is as far as I want to take the video lecture. This should cover special problem 10.1. I don't remember if it covers 10.2, but it does cover 10.1. And so Tuesday, Wednesday, and Thursday of next week, all we're going to look at is how do we take that enthalpy of reaction and adjust it to any particular temperature that we're interested in, because we're usually not interested at 25 degrees C. That step takes a fair amount of work, but we've already seen all the tools to do it, so it's just kind of tedious bookkeeping. So I hope everybody has a great weekend. Enjoy your day off on Monday, and I will see you on Tuesday. Only 3 days left. Have a great weekend, everybody.